In this video, we're going to discuss projectile motion. Here we have a dynamite blast. A dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second. The height of the object in feet after t seconds is given by the following position function. S of t equals 160t minus 16t squared. So the first part of this question, we're going to discuss how high does the rock go? Well, before we really get into anything, one thing that's generally pretty important for us to do is to consider what our function looks like, especially in an application problem. And if we were to graph this on the calculator, we would get a parabola. We'd find that S is equal to this function of t here, 160t minus 16t squared. That's what I plugged into my y equals, measuring time on the x-axis and position on the y-axis. So very easily we can see how high does the rock go. That's going to be this maximum, right? That's my maximum height. S represents height. And we can do that with algebra because this is a quadratic function. And if you remember from algebra, you can say negative b over 2a. That's going to give you the time at that maximum height. You would plug that value in to find your actual maximum height value. But we want to do this using calculus. So what we know is that the derivative of position is velocity. And at that moment, right when we're at that max, we are going up, we have a positive velocity. We are going down, then we have a negative velocity. So what is the velocity at that maximum? And in this case, we're going to see that the velocity right here at the max, that derivative, velocity is the derivative or the instantaneous rate of change, would be 0. So in order to do this, we would say, well, S prime of t equals my velocity function, and that is 160 minus 32t. And I just did that by taking the derivative and using my power rule. So if we want to know the max height, is going to occur when the velocity is equal to 0. So 0 equals 160 minus 32t. Solving that, I'll factor 32 out. So that's 32 equals 5 minus t, or at t equals 5. So at t equals 5, we reach the maximum height. This says how high does the rock go. So that maximum height is going to be some value over here on my y-axis. And in order to find that, I'm going to take t equals 5 and plug it into my function. So S of 5 is 160 times 5 minus 16 times 5 squared. S of 5 equals 400. So at t equals 5 seconds, we know the max height is 400 feet. Now let's continue with our second part of this question. We have our position. We determined in part A the velocity. At this point, the question says, what are the velocity and speed of the rock when it's 256 feet above the ground on the way up and on the way down? So we need to find velocity, right? So we're looking for velocity. That means we need a time. We are not given a time in part B. All we are given is that we know it's height above ground. And remember, height is position. So when the height or position is 256, I can find a t value. If I know that t value, then I can determine velocity at that same t value. All right, so to do this problem, we're going to say 256 equals my height. S of t is 256, which means I have 160 t minus 16t squared is equal to 256. So this is a quadratic equation. I need to solve this equal to 0. So we have 0 equals negative 16t squared plus 160t minus 256. From here, in order to solve this, I'll factor out a negative 16, which leaves me with t squared minus 10t plus 16. And this factors, dividing by negative 16 on both sides, that would go away. 0 divided by negative 16. And it would factor, we would get t minus 8, t minus 2. So the position, or the height, is 256 feet at t equals 2 and 8 seconds. So we know we are at that height at t equals 2 seconds and at t equals 8 seconds. So v of 2, plugging 2 into velocity, is 160 minus 32 times 2, which gives me 96. So that's a velocity that is 96 feet per second. And the velocity at 8 seconds, 160 minus 32 times 8, we end up with negative 96. Negative 96 feet per second. So this positive velocity is the velocity when we are traveling up, and the negative velocity is the velocity when we are traveling down. So the velocity is positive at t equals 2 seconds and negative at t equals 8 seconds. We're traveling up for the first half, we've reached the maximum, and then we have turned around and we're coming back down. Remember, the absolute value of velocity equals speed. So the speed at both of these, the speed is just 96 feet per second. And if we are to go and consider our position function graph, so remember we have the graph of a parabola. One thing we have identified is that t equals 5, we have a height of 400, but at 256, which is what we were just talking about, 256, that occurs at approximately t equals 2 and t equals 8. You'll notice we're going up at t equals 2, we have a positive slope, positive velocity. And at t equals 8, we're going down. We have a negative slope, rate of change, or a negative velocity. All right, and then again, just reinforcing from part A, at t equals 5, we had a horizontal velocity, a maximum value occurred. All right, 2 more parts to this problem. Part C of this problem asks us, what time or what is the acceleration of the rock at any time t during its flight after the blast? What we decided or determined in the previous video is that the derivative of velocity gives us acceleration. So v prime of t, the derivative of velocity, gives us my acceleration function, which is negative 32. The derivative of 160 is 0, and the derivative of negative 32t is just negative 32. So what does this tell us? Well, we have a constant negative acceleration. The acceleration is always downward, and that is because of the effect of gravity on the rock. As the rock rises, it slows down. As it falls, it speeds up. So the acceleration is negative 32, and that would be feet per second squared. So think about it. We started our position function, S was in feet. We differentiated with respect to time, and we got velocity, which is feet per second. Differentiating feet per second with respect to time is feet per second, or feet per second squared. Right? So a constant negative acceleration, negative 32 feet per second squared. The last part of this question, when does the rock hit the ground again? Well, we have to think about what we are being given in this question. We're being asked to find when, right? That's what we don't know. So we do not know time. So we must have a position, a velocity, or an acceleration. So when the rock is on the ground, what we know is that the height, or the position, is equal to 0. So this means find the time when the position is equal to 0. And this will need to be a positive time because we're not going to have time before the launch. So sometimes when you solve this, you could get two negative, or a negative and a positive value. In this situation, you need to make sure that it's a positive time value that reflects time that has elapsed after the launch. So this means we are taking that position function and setting it equal to 0. And this should be easy to solve. This is just an algebra problem here. So I will factor out 16t. That leaves me with 10 minus t squared. Or I'm sorry, that would just be a t, 10 minus t. And solving this equal to 0, I would get 16t equals 0, or just t equals 0, and t equals 10. Now, t equals 0, we know it's already on the ground, so at t equals 10. So 10 seconds after launch, it lands on the ground. And that is in a line with what we looked at in our picture. So we start on the ground, we have an increasing velocity until we reach our max at 5 seconds, which is 400 feet. Right at that moment, the tangent line would be horizontal or have a slope of 0, and then the rock is falling until we reach t equals 10. And just to include a little bit more, because I know you guys are dying for it, if you think about velocity here, velocity is a linear function with a negative slope. If we were to graph velocity on the same plane as our position function, we would end up with something that looks like this. We have a positive velocity. Notice the whole graph is above the x-axis here between 0 and 5. And then at t equals 5, from 5 to 10, we would end up with negative velocity values. So just an interesting thing I wanted to point out relating that velocity to our position. So any questions, feel free to email me. I hope this helps. I'll probably do one more application video in this series.